So we start with introduction. Nuclear fusion process that is occurring inside the core of the sun. The specific type of fusion that occurs inside of the sun is known as proton-proton fusions. Inside the sun, this process begins with proton, which is supplied along hydrogen nucleus, and through a series of steps. These protons fuse together and are turned into helium. This fusion process occurs inside the core of the sun, and the transformation results in a release of energy that keeps the sun hot. The resulting energy is radiated out from the core of the sun and moved across the solar system. It is important to note that the core is the only part of the sun that produces any significant amount of heat through fusion. It contributes about 99%. The rest of the sun is heated by energy transferred outward from the core. So the reason for choosing this topic and is relevant to modern physics, we choose this topic because nuclear fusion is one of the most important energy producing process in this universe. It explains how the sun and other stars generate energy continuously for billions of years. This topic is highly relevant to modern physics because scientists are currently researching fusion as a future clean and sustainable energy source. Fusion technology has the potential to produce large amount of energy with minimal pollution and less radioactive waste compared to nuclear fusions. Understanding solar fusion also helps physics study stellar evolution, particle physics, and energy conservation. So next, I will explain the methodology we use for gathering information for this independent learning topic. To complete this research, we collect information from several reliable sources such as scientific journals, articles, education websites, online videos, and documentaries. We compare information from different references to make sure the fact we use is accurate and easy to understand. Important concepts we summarize and simplify so that they could be explained clearly during this presentation. This method helps us gain a better understanding about how nuclear fusions happen in the sun and why is it important in modern physics. So next, I will explain the methodology we use for gathering information for this independent learning topic. To complete this research, we collect information from several reliable sources such as scientific journals, articles, education websites, online videos, and documentaries. We compare information from different references to make sure the fact we use is accurate and easy to understand. Important concepts we summarize and simplify so that they could be explained clearly during this presentation. This method helps us gain a better understanding about how nuclear fusions happen in the sun and why is it important in modern physics. So next, I will explain the methodology we use for gathering information for this independent learning topic. To complete this research, we collect information from several reliable sources such as scientific journals, articles, education websites, online videos, and documentaries. We compare information from different references to make sure the fact we use is accurate and easy to understand. During the independent learning process, we faced several challenges. The first challenge was understanding complex nuclear reaction and difficult physics terms. To solve this problem, we refer to education video, diagram, and simple explanation from trusted sources. The second challenge was finding relevant and accurate sources of information. We overcome this by using trusted academic websites, scientific articles, and textbooks. The third challenge was confusion between nuclear fusion and nuclear fission because both processes involve nuclear energies. To solve this, we compare both processes using tables, examples, and diagrams to clearly identify their difference. This challenge helped us improve our understanding and research skills throughout this project.
So, what is nuclear fission in the sun? Nuclear fission in the sun is the process that powers a star by combining hydrogen nuclei to form helium, releasing immense energy. Modern physics explains this through the photon-photon chain reaction, quantum mechanical theory, and Einstein mass energy equivalence. The first core concept is photon-photon chain. In the sun core, immense gravitational pressure and temperature reach roughly 15 million Kelvin. Under this extreme condition, hydrogen atoms are stripped of their electron, creating a plasma of free photons because photons have a positive charge. They naturally repel each other. In the sun core, hydrogen nuclei fuse together under very high temperature and pressure to form helium. This process is called nuclear fusion. This happens because the sun is extremely hot, about 15 million Kelvin. Hydrogen atoms become plasma, meaning protons are free. Even though they repel each other, the pressure is so high that they are still collide and fuse in types called the photon-photon chain. However, they move fast enough to overcome this and fuse through a multi-step process called the photon-photon chain. Step 1. Two photons fuse to form a deuterium nucleus, relating a positron and neutrino. Two protons fuse to form a deuterium and release the positron and neutrino. One photon changes into a neutron during this process, forming a heavy nucleus called deuterium. Step 2. A deuterium nucleus collides with another photon to form a helium-3 nucleus, releasing a gamma-ray photon. Deuterium combines with another photon to form helium-3 and release gamma energy. This step adds another photon and energy is released as light in the form of gamma ray. Step 3. Two helium-3 nuclei fuse to create a stable helium-4 nucleus, releasing two excess photons to continue their cycle. Two helium-3 nucleus combine to form helium-4 and release two photons. This is the final step, producing a stable helium nucleus and restarting the cycle. Next, modern physics laws and theory. Solar fusion relies on a few fundamental principles of physics, that is, mass energy equivalence, quantum tunneling, and Coulomb's law. First, mass energy equivalence. Although helium is a final product, its mass is slightly less than the combined mass of the 4 original photons. This meeting mass is converted directly into energy according to Einstein's famous equivalence. A small amount of mass is converted into a large amount of energy using Einstein equivalence. The final helium nuclear weight is slightly less than the original photon. That missing mass becomes energy. Second, quantum tunneling. According to classical physics, the sun's core is not quite hot enough to overcome the electromagnetic repulsion of 2 photons. However, due to quantum mechanics, particles behave like waves. This allows protons to tunnel through the energy barrier and fuse. The phenomenon explained by the principle of quantum probability. Photons can still fuse even if they don't have enough energy to overcome repulsion. This happens because particles can tunnel through barriers due to quantum physics. And lastly, Coulomb's law governs the electrostatic repulsion between the positively charged photons, defining exactly how much heat and pressure are required to push them close enough for the strong nuclear force to bind them together. Photons naturally repel each other because they have positive charge. This repulsion is what makes fission difficult and requires extreme temperature and pressure. So there are 4 most important of nuclear fission in the Sun. There is stellar engine, source of Earth energy, element migration, and template for clean energy. First is stellar engine. Fusion stabilizes the Sun through hydrostatic equilibrium. The outward pressure created by the emitted heat of fusion perfectly balanced an inward pull of gravity, keeping the Sun stable for billions of years. Fusion keeps the Sun stable by balancing gravity. The energy from fusion pushes outward and stops the Sun from collapsing. Second, source of Earth energy. The gamma ray produced in the core bounce their way to surface, cooling into the vision light and heat that drive Earth water, ocean current, and photosynthesis. Fusion produces sunlight that reaches Earth. This energy drives water, climate, and allow life to exist. Third, element creation. Fusion in stars is responsible for the creation of heavier elements. The helium produced in the Sun and eventually carbon and oxygen in larger stars provide the building block for the universe. Fusion creates new elements in stars. Light elements like helium are formed in the Sun and heavier ones formed in larger stars. And lastly, templates for clean energy. Understanding solar fusion allows modern physicists to research and develop artificial nuclear fusion on Earth. Facilities like the International ITER tokamak aims to harness this same reaction to provide a limitless zero carbon and highly efficient source of global energy. Scientists try to recreate fusion on Earth for clean energy. Projects like ITER aim to produce unlimited pollution-free electricity. Next is example related to nuclear fusion in the Sun. There is photon-photon chain reaction. This is the primary natural reaction in the Sun. Deep within the solar core temperature reach 15 million degrees Celsius, stripping electrons from hydrogen gas to create a plasma. Over a 3-step process, 4 hydrogen protons fuse into a single helium-4 nucleus, converting a fraction of their mass into heat and light via Einstein equation. This is a natural process that powers the Sun. 4 hydrogen atoms combine into helium and release huge energy. Next is earthly artificial sun reactors. Because Earth cannot replicate the Sun's massive gravitational pull to hold the plasma, scientists use massive magnetic field in devices like tokamaks and stellarators to contain it. Examples include the experimental East Tokamak in China and the DIIIT facility in San Diego, both of which have set records for stabilizing artificial fusion plasma. Scientists use magnetic field to control fusion on Earth. Devices like tokamaks hold hot plasma because we cannot use gravity like the Sun. Next is earthly artificial sun reactors. Because Earth cannot replicate the Sun's massive gravitational pull to hold the plasma, scientists use massive magnetic field in devices like tokamaks and stellarators to contain it. Next, the ITER project. Located in Calerature, France, ITER is the world's largest magnetic confinement plasma physics experiment, funded by a coalition of countries including the EU, US, China, and Russia. It is designed to replicate the Sun's core reaction for generating large-scale clean energy. ITER is a global experiment to test fusion energy. This is designed to imitate the Sun process for future energy production. Next, the ITER project. Located in Calerature, France, ITER is the world's largest magnetic confinement plasma physics experiment, funded by a coalition of countries including the EU, US, China. Other than that, initial confinement fusion at facilities like the National Ignition Facility (NIF) in California, scientists simulate the Sun's extreme pressure by blasting a tiny pellet of hydrogen fuel with high-powered laser to trigger the fusion reaction. Lasers are used to compress fuel and trigger fusion. This method imitates the Sun's pressure using powerful lasers. Other than that, initial confinement fusion at facilities like the National Ignition Facility (NIF) in California, scientists simulate the Sun's extreme pressure by blasting a tiny pellet of hydrogen fuel with high-powered laser to trigger the fusion reaction. Lasers are used to compress fuel and trigger fusion. Lastly, sunlight and fossil fuels. A broader example of solar fusion is that with sunlight itself. The energy released by fusion in the Sun will travel to Earth and fuels our ecosystem, weather system, and it even stored as excellent solar energy in fossil fuels. Fusion in the Sun produces energy that reaches Earth as sunlight, and this energy also indirectly supports fossil fuels. Sunlight from the Sun powers sunk through photosynthesis. Over millions of years, dead plants and organisms are buried and transformed into fossil fuels like coal, oil, and gas. So fossil fuels are actually store solar energy that originally came from nuclear fusion in the sun. So now, how nuclear fusion in sun applied in daily life? Nuclear fusion in the sun affect our daily life because it produces the sunlight and heat that makes life on Earth possible. The energy released from fusion support photosynthesis, plants make food and oxygen. Sunlight helps plants make food. Plants use solar energy to produce oxygen and glucose. Other than that, solar panel generate electricity. We use solar panel to convert sunlight into electricity. It is a direct use of energy from nuclear fusion in the sun. And next, weather and water cycle. Sunlight heats Earth and drives the rain, wind, and ocean. Sunlight drives weather system on Earth. It heats oceans, creates wind, and causes rain. And next, human health. Sunlight helps our body pressure vitamin C. Sunlight helps our body produce vitamin C. It is important for bone health and immunity. And lastly, food chain. Almost all living things depend on solar energy directly or indirectly. Almost all life depend on energy from the sun. Energy from fusion start the entire ecosystem chain. So this is two most recent advancement in nuclear fusion in the sun. That is China's artificial sun breakthrough. Scientists in China successfully pushed fusion plasma beyond a major limit that has stopped fusion reactor for decades. This is considered one of the biggest recent breakthrough in fusion research. China achieved a major breakthrough in fusion stability. They managed to keep plasma stable for a longer time than before. And secondly, Germany won the Steel 7X reactor. Scientists in Germany improved a special fusion reactor called the Wendelstein 7X, which can keep plasma more stable for fusion reaction. Germany improved a special fusion reactor design. It helps scientists understand how to keep fusion plasma stable more efficiently.
Now, I will present about self-development for a career in modern physics, specifically in fusion physics and fusion energy. First, there are several careers related to fusion physics. A fusion reactor engineer designs fusion reactors and plasma confinement systems. A fusion plant technician operates and maintains fusion reactor equipment. A material scientist develops heat and radiation resistant materials for reactors. An optical control system engineer develops laser systems for fusion experiments, while a superconducting magnet engineering creates strong magnets to contain plasma in fusion reactors. To succeed in these careers, important skills and interests include strong physics and mathematics knowledge, problem solving and analytical thinking, interest in technology and clean energy, as well as teamwork and communication skills. Next, for skills needed in career planning, students should improve academic performance in physics and mathematics, develop technical and research skills, gain hands-on experience through projects and internships, and continuously update their knowledge about fusion technology advancements. Important skills in this field include plasma science and fusion reactor knowledge, advanced mathematical and analytical skills, computer simulation, modeling and data analysis, reactor safety and technical operation skills, as well as research, teamwork, and communication abilities. For career planning, students should strengthen their understanding in physics and mathematics, learn programming and simulation software, join internships, projects, or laboratory activities, and attend workshops and seminars on fusion technology. Continuous self-development is also very important in modern physics. It helps keep knowledge and skills updated, adapt to new fusion technologies, improve employability and career growth, enhance problem-solving abilities, and encourage innovation in clean energy research. However, there are also challenges in pursuing this career. Complex physics concepts can be overcome by studying step by step and seeking guidance. Strong mathematical demands require regular practice. Heavy workloads can be managed with good time management, while rapid technological changes require continuous learning and skill upgrading. In conclusion, careers in fusion physics require strong knowledge, technical skills, and continuous self-development to contribute to future clean energy development.